Welcome to the presentation of our online course, Bioprocess Engineering Basic Principles. Through our online courses series, you learn the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and animal cell cultures processes. For more details, visit us at bioprocessengineeringonline.com. Bioprocess engineers design and scale up bioprocesses, encompassing both upstream and downstream unit operations. At the core of these processes is a transformation step, catalyzed by enzymes, microbial cells, or animal and plant cells. The key challenge for bioprocess engineers is to optimize technical efficiency, cost effectiveness, and environmental sustainability throughout the entire production system. To accelerate process design and reduce the costs associated with development, bioprocess engineers are increasingly relying on simulation models. The most effective of these are knowledge-based models that incorporate the fundamental physicochemical principles governing bioprocess unit operations. These models enable engineers to predict the impact of operating modes and process variables on bioprocess performance and to optimize process conditions accordingly. Knowledge-based models are built upon a deep understanding of the key biochemical and physical phenomena that govern the behavior of bioprocess operations. All bioprocess operations are influenced by four fundamental phenomena: biochemical reactions, mass transfer, heat transfer, and fluid flow. Together, these core processes determine the kinetics and overall performance of bioprocess operations. Constructing a simulation model involves formulating mathematical relationships that describe the temporal changes in component concentrations or temperature. The key governing phenomena, biotransformation reaction, fluid flow, mass transfer, and heat transfer, are first characterized by their underlying thermodynamic and kinetic laws, which define the rates at which these processes occur. These laws are then integrated with mass and energy balance equations, which express the fundamental principles of conservation. This integration is summarized by the balanced thermodynamic kinetic modeling triangle, providing a structured framework for developing predictive simulation models. In this course on the fundamental principles of bioprocess engineering, you will learn the essential concepts and methods for building bioprocess simulation models based on the balanced thermodynamic kinetic triangle. You will explore how to formulate mass and energy balances, the key thermodynamic and kinetic laws that govern enzymatic and cellular transformations, fluid flow, mass transfer, heat transfer. These foundational elements provide the tools to model, analyze, and optimize bioprocess operations effectively. The course is structured into 8 sessions: mass balances, energy and heat balances, fluid flow, residence time distribution, mass transfer kinetics, heat transfer kinetics, enzyme kinetics, cellular kinetics. The 8 sessions can be taken independently. In bioprocess modeling, mass balance equations are among the most widely used tools for expressing the fundamental principle of mass conservation. In Session 1, you will learn the 2 main types of mass balances: initial final mass balance and instantaneous mass balance. How to write mass balances for both total mass and individual components. When and how to apply each type of mass balance, depending on the modeling objective. Energy balances are similarly used in bioprocess modeling to express the fundamental principle of energy conservation. In Session 2, you will learn the 2 types of energy and heat balances: initial final and instantaneous balances. How to formulate energy and heat balance equations. How to apply these balances to evaluate energy consumption, predict time-dependent temperature changes during bioprocess operations. Session 3 explores the key concepts and methods used to describe fluid flow dynamics in bioprocess equipment. Topics include rheological properties of fluids, momentum transfer rates, fluid velocity distributions, laminar and turbulent flow regimes. Special emphasis is placed on understanding how fluids flow in pipes and agitated tanks, as well as determining the energy requirements for operating this equipment efficiently. Residence time distribution, RTD, is a widely used methodology in process engineering for analyzing the impact of fluid flow patterns on the performance of continuous unit operations. In Session 4, you will learn what the RTD function of a process unit represents, how to experimentally determine the RTD, the main flow models used to characterize and interpret equipment RTD behavior. Mass transfer is often one of the most limiting phenomena in bioprocess unit operations, as it directly constrains both the rate and overall performance of the process. In Session 5, you will learn the mechanisms and kinetic laws governing mass transfer by diffusion and convection, how to evaluate mass transfer resistances and rates in multi-phase systems, how concentration gradients are established and evolve within these systems. Heat transfer is a major limiting phenomenon in thermal unit operations, as it directly impacts both the rate and efficiency of the process. In Session 6, you will learn the mechanisms and governing laws of heat transfer by conduction, convection, and radiation, how to evaluate heat transfer rates and resistances in multi-phase systems, how temperature gradients are established, and how they evolve over time within these systems. The kinetics of enzymatic reactions is the primary phenomenon governing the performance of enzymatic reactors. In Session 7, you will learn the rate laws for both enzyme-catalyzed reactions and enzyme denaturation, how these rates are influenced by the concentrations of substrates and products, temperature and its effect on enzyme activity and stability. The rates of cellular conversion reactions are the primary governing phenomena in microbial fermenters and animal cell culture bioreactors. In Session 8, you will learn the kinetic laws governing cell growth and death, nutrients consumption, production of metabolites and recombinant proteins, how these rates are influenced by the concentrations of nutrients and metabolites in the surrounding medium. The course resources include recorded slideshow presentations covering all the investigated basic principles. You will also perform application exercises and problems on specially designed spreadsheet templates, featuring a green-red correction system that provides immediate feedback on the accuracy of your inputs. You can take this course in one of two formats: individually, progress through the sessions, and schedule personalized one-on-one video meetings with your tutor. In small groups, 2 to 5 participants, learn collaboratively and benefit from interactive group video sessions guided by your tutor. Regardless of the format, you'll have the flexibility to tailor the course to your individual learning pace and preferences. For further information on the course, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com.